Next speaker is Congyu Liu, and he is currently a PhD student in computer science from Purdue University. And he will present his work about Kit, a dynamic testing framework that discovers bugs in OS-level virtualization mechanisms, such as Linux namespaces. So, if you're ready, you can go ahead.
Okay, then I'll start. So thanks our session chair for introduction. Hi everyone. Today I'll be presenting our work, Kit, a system that is very effective at finding functional interference bugs in OS-level virtualization, such as Linux namespaces. This is a work done by me, my colleague Sishuai Gong, and my advisor, Pedro Fonseca. Containers are widely used today. Developers use containers to easily deploy applications, and as a result, they have been widely used in data center and the cloud. A recent survey shows that 79% of organizations use containers in production and 44% using them for most or all production applications. So why are containers so popular? A simple answer would be that they can share the same kernel efficiently and securely. This requires isolation between containers, but who's providing it? So let's take a look at this well-known diagram. Containers runs on top of container engines, which runs on top of kernel. We might have the impression that container engines such as Docker provide isolation between containers, but actually it is the kernel which does it. Specifically, the resources of different containers are isolated by the kernel. The kernel puts a wall between containers, making sure that a container can access the resources that belong to itself, such as files or network stack, and cannot access the resources across the wall in other containers, unless through some secure channels. However, if the kernel implementation is buggy, this wall can have holes. So this allows functional interference bugs, in which a container can modify the kernel resources of other containers and affect the syscall results. Functional interference bugs can have serious impact. The interference allows a container to cause integrity violations, such as data corruptions, or cause denial of service to other containers. The interference can also let a container accidentally leak information to another container. Let's take a look at an example of a real-world functional interference bug. So as a background, network configuration should be isolated for containers. In other words, if a container writes to a network configuration, this should not affect the configuration read from another container, and also its network functionality. However, this isolation does not hold for an important network configuration, NF contract max, which limits the firewall connection tracking table. And this is the bug in Linux namespaces. Because of this missing isolation, any update on this configuration will be applied to all containers in the same kernel. In some cases, this bug could be exploited to launch denial of service attack. So how does this bug happen? The root cause is that all containers share the same global variable. Given the impact we just saw, detecting such bug is very crucial. But unfortunately, this is very difficult. The main reason is that many functional interference bugs, just like the example we saw, are semantic bugs. They do not cause crashes. Also, they do not involve memory errors or data races. These semantic bugs are very challenging to detect. They cannot be detected by traditional dynamic bug detectors, such as memory sanitizers or crash checkers. While static analysis can detect semantic bugs, they could produce high false positives, mainly due to the complexity of the kernel, which extensively relies on function and data pointers. So unlike these approaches, we check if a container's syscall traces are impacted by another container. So this approach has two benefits. First, it can detect semantic bugs that do not incur explicit errors because it analyzes the communications between user and kernel rather than the internal errors. Plus, the reports simplify the bug analysis since they include the consequences, such as what system calls are affected. But how can we know if the system call results are affected by another container? So the observation is that if there's a functional interference bug, some other containers can change the syscall results of other containers. So for instance, in the previous example, the value of the network configuration changes to the value written by the other container, as shown on the left side. If we have another execution without the container that updates this configuration, as shown on the right side, then the configuration read from the container is different from the one on the left side. So with this observation, our approach is to compare system call traces across executions. In one execution, we run program A first, then program B. And in another execution, we only run program B. Then we collect the syscall traces of program B in both executions. If they're different, it is likely that program A causes interference on program B. However, simply comparing two traces is not practical because there are two exceptions. The first exception is caused by non-deterministic syscall results, meaning that their values might be different across executions without any functional interference bug. So for example, syscall traces might contain timestamp, which can be slightly different across executions. They can cause the traces to be different, but that does not imply a bug. So as you can see from this example, the syscall trace difference due to such non-determinism should not be reported, and we should be able to identify and ignore them. Our idea is that non-deterministic results can be identified by rerunning the same execution for multiple times. So here we run program B alone without any other containers for 2 times. In this case, B can never be affected by any functional interference bug. If we still find that the traces are different, then we conclude that such difference is caused by non-determinism, so we don't report such results. And another exception is caused by the non-isolated kernel resources. So some resources are deliberately non-isolated in Linux namespaces. System calls on these resources can interfere, and these are expected behaviors, not bugs. So we address this problem using 2 techniques. First, we use a strong container configuration to prevent accesses to these non-isolated kernel resources. Second, we only check the system call results on the isolated resources in a specification. And this specification does not need to be complete. It can be progressively refined. So now that we have a method to reliably detect functional interference bugs given a test case, the next problem is, how can we generate effective test cases? So in case you wonder, what are effective test cases? They should be test cases that trigger inter-container kernel data flows. These low-level data flows are necessary for the high-level interference to happen. So for instance, in the previous example, one container first updates a shared variable nf contract max, which is then read by another container. These memory accesses are inter-container kernel data flows. So now our goal is to generate test cases with more and various inter-container kernel data flows. This is actually similar to the goals of some concurrency testing tool, so which we can learn and benefit from. And here is our approach. The input is a set of programs that can be generated from OS fuzzers. And the output and then we'll generate pairs of programs that have kernel data flows. So now the question is, how do we know and how do we predict the kernel data flows between two programs? Our solution is to predict kernel data flows by analyzing the kernel memory traces. First, for each program, we profile the kernel memory accesses triggered by it, such as which kernel variables are accessed. Then, if two programs access the same variables during profiling, we will pair them, assuming the kernel data flows will happen when they're running together on the shared kernel. We implemented the kit in 8,000 lines of code. We wrote this partial specification, including many kernel resources that should be isolated by Linux namespaces. Kit also supports cluster-similar test reports to reduce analysis effort. In evaluation, Kit found 9 bugs in Linux kernel 5.13. The consequences of these bugs include allowing one container to disable network fastpass for all other containers, or a container leaks network statistics to other containers, and also resource contention, such as containers cannot use the same network address in some network protocols. To see how effective is our test case generation, we compare with random test case generation, which will randomly pair test programs to build test cases. The left figure shows that random approach can find 5 bugs. The right figure shows that Kit test case generation is much more efficient than random generation. This shows that Kit can not only find more bugs than random, but also use much fewer test cases and executions. Lastly, we evaluate the effectiveness of result filtering and reports clustering. After running 1 million test cases without result filtering, the number of test reports are a bit over 15,000. After we enable result filtering, the number of test reports dropped to about 800. After clustering similar test reports, we got 32 clusters, and only 4 false positives. This shows that result filtering and test report clustering can significantly reduce the analysis effort. So in conclusion, OS-level virtualization suffers from functional interference bugs, and many of them are semantic bugs. To address this issue, we propose an approach that is able to trigger and detect such type of bugs. In evaluation, we showed that such differential testing techniques is able to scale to Linux kernel and be able to find unknown functional interference bugs, and some of them are fixed. Kit artifact is available at GitHub, so if you are developers who are building or changing things that affect namespaces, or if you are users who care about resource isolation, just please try it out. Thank you for listening. I'm happy to take questions.